Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on November 19, 2025, about 3 days ago. This paper introduces a large-scale recipe for turning everyday human first-person videos into robot skills, using over 1,000 hours of in-the-wild footage plus more than 20 hours of task-specific demonstrations to train a single policy that follows language instructions, learns from just a few robot demos, and stays robust to new settings. The paper is titled In-On, Scaling Egocentric Manipulation with In-the-Wild and On-Task Data. And as we will see, the implications for training general-purpose humanoid manipulation are quite significant. Alright, Figure 1 lays out the whole story of how everyday human videos turn into robot skills. The left panel shows the collection hardware, including head-mounted cameras like Aria Glass and Apple Vision Pro, plus humanoid robots that record both vision and motion. The central panels illustrate pre-training on over 1,000 hours of mixed egocentric data, then post-training with on-task demonstrations to shape the human zero-base model. The right panel highlights the payoff, showing robots that follow unseen language instructions, learn from just a few demos, and execute complex tasks in the real world. Figure 2 spells out how Human Zero turns mixed human and robot data into one policy. The left block shows Sig Lip taking egocentric images and a language command, feeding a pre-trained vision language model that outputs tokens. These tokens and poses for both humans and robots are projected into a single latent state, which the flow matching action expert turns into robot actions. The right block adds domain adaptation, where a discriminator with gradient reversal forces the shared representation to hide whether it came from a human or a robot, so transfer becomes easier. Well, Figure 4 clarifies how much human versus robot experience actually feeds the model. The top row shows pre-training, where human videos make up about 85% of the raw data, but the sampling weights increase robot data to nearly 40%, so the model does not ignore it. The bottom row shows post-training, where human and robot demonstrations are more balanced, yet humans are sampled more heavily at roughly 70%. This mix encourages embodiment alignment, while still anchoring behavior in rich human egocentric data. Alright, Table 1 summarizes how the different policies perform across the 4 manipulation tasks, both in distribution and out of distribution. Human Zero sits at the bottom row and achieves the highest scores almost everywhere, from perfect or near-perfect grasping to the best burger assembly and pouring rates. The gap is especially clear in multi-object grasping, where Human Zero reaches full success on unseen objects and scenes. These results show that scaling with large human video plus on task data really lifts both language following and robustness. So while Table 1 compared methods across tasks, Figure 8 zooms in on single object grasping as the amount of robot data varies. The curve shows that Human Zero consistently beats the baseline policy Pi0 at every demonstration percentage. The gap is largest when only about a quarter of robot demonstrations are used, which indicates that rich human data strongly regularizes learning in the low data regime. As robot demonstrations increase, both policies improve, but Human Zero still keeps a small edge. Alright, Figure 8 focused on how extra robot demonstrations change grasping success, and Table 2 now probes why the domain adaptation step matters. Table 2 reports staged success rates for the bimanual pouring task, split into right grasp, left grasp, and the final pour, plus the overall success rate. Adding the discriminator hardly hurts right-hand grasping, but clearly boosts left-hand grasps in the actual pour stage, so the total success rises from about 15% to roughly 25%. So, while Table 2 showed gains in pouring performance, Figure 7 explains how the discriminator actually reshapes the internal representation. The plot compares predicted probabilities that a sample is a robot or a human embodiment. With the discriminator, both robot and human points cluster around 50%, which means the features are domain invariant. Without the discriminator, probabilities jump to near 0 or 100%, so the model trivially distinguishes embodiments and cannot transfer as well. So the big takeaway is that large-scale first-person human video, when split into in the wild and on task streams and aligned with domain adaptation, really can teach humanoids flexible, language-driven manipulation. More broadly, it suggests a path to train general-purpose home and factory helpers from everyday human experience. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.